All right. Thanks for joining me. I'm Dr. Ryan Hayes at Andrews University in the Department of Chemistry. And this is our lecture 57, dealing with electrochemistry and general chemistry, Chem 132. Little question to get us going here. How many electrons are transferred in the following reaction? This is important because we need to be able to quickly tell this for some of the equations that we're going to do, because today in this lecture, we're going to learn about the Nernst equation and concentration cells. And eventually we want to use this information to really get in and understand batteries and actually corrosion, spontaneous chemical reactions. So let's go back to this question. I can always pause and see if you can guess the right answer. Well, here's how I figured out. I kind of jump in and I'm going to go to my little iPad here, and I look at probably one of the easiest thing is this looks balanced, and it is, so that's very important. We need to have a balanced electrochemical reaction, and if you look at the chlorides going to the other here, this chlorine, we've got a 6 negative charge going to 0. In order for that to happen, there must have been 6 electrons that were given off. So I would pick D, 6 electrons, and that's the correct answer there. Okay, so these are important things to kind of look at. That was an easy one. I could have found the thing that was being reduced, which was actually chromium, and if you go and solve that, that's +6. And then I've got 2 of those, so that's a total of +12 for the chromium, and then ends up at +6 on the other side, because I've got 2 times a +3. So that gives me a total of +6 on this side. And if I look at the oxidation state of chromium, it is a +6, okay? Trust me. And that means 6 electrons were gained in order to go from +12 to +6. So there's a couple of ways one could look at those. All right. So let's go on though. Another quick question. Do you remember what happens if you double an electrochemical reaction? If you double it, do you double the voltage? Half it? Does it stay the same? Square it, square root it? What do we got? Well, if you remember that, it stays the same. That's right, it doesn't matter how you scale it, and I explained that in another video why that is. All right, so today we're going to look at how do you determine, using this Nernst equation, the cell potential under non-standard conditions. All right, and we kind of did this in one of our labs, and we're also going to see the connection between free energy and electrochemical potential and equilibrium, leading us into a little interesting discussion on what a concentration cell is. Now, this information is very relevant and leads into corrosion science, batteries, and all the battery science that's out there. I'm going to probably leave those 2 last things for another video. Let's focus on the Nernst equation and some of these other topics for today. Now, in chapter 16, we learned about free energy, and specifically free energy under non-standard conditions. And there was this Gibbs Free Energy equation that we learned, where under non-standard conditions, that's the delta G here, is equal to the free energy of a chemical reaction under standard conditions. That's what that little circle's there for, right? And then we would add in this term, RT ln of Q, where Q is the equilibrium constant under non-standard conditions, or the equilibrium ratio, products divided by reactants. All right, now recently we've been learning that we could see the connection between free energy and the electrochemical potential. It's equal to -n, number of electrons transferred, times F, Faraday's constant, times the electrochemical potential for a cell, oxidation plus the reduction. So if we just replace that in both the delta G and the delta G standard, but leave in the little standard symbol here, see the connection, match, match, we can modify then, well, we actually just leave this term in here, RT ln of Q. Now we can simplify this equation a little bit more by dividing through by -NF. So that gives us the electrochemical potentials by themselves, and they divide out, and we end up with this minus RT over NF times the natural log of Q. Well, what you will often see for the Nernst equation is that since R is 8.314, 5, if you want some more significant digits, joules per Kelvin, mole is actually in there as well. And temperature often at 298 for our standard conditions. Faraday's constant, 96,485 joules per volt. Then if we were to plug those in, we could multiply R times T, divide by F, leave N alone because we don't know what that is for our chemical reaction. We can simplify this equation once more by replacing those three numbers with 0.0257 volts. So V is for volts, N is the number of electrons that are being transferred, and Q then is our products and reactant ratios. So we have to go figure those out for whatever the particular problem is that we're dealing with. So this is very helpful because the Nernst equation really gives us a tool to predict the potential, the voltage you would get when you're not at standard conditions, which is a lot of the time. So just to review, then the Nernst equation is the ratio of the concentration of the products divided by the reactants. All the same things that we've learned about equilibrium constants and Q's and relating to that before. All another chapter, we've already spent months on that. Okay, so E without the naught, now sometimes the subscript cell will be in there and sometimes it won't. Don't worry about that part. What we want to worry about is whether it has the naught symbol or not. If it has the naught symbol, then we're talking about, hey, you can go look up these reduction potentials, oxidation potentials on tables, add them together. This is what you would put here for the E naught, okay? So if we're feeling really good, we'll put cell in there, but it's really the E naught. We mean the total potential of the cell. All right, N, number of electrons. You have to balance the chemical reaction. We've been spending all week learning how to identify oxidation reduction half potentials in the reactions and then balancing them. It's from the balanced chemical reaction, the number of electrons that are given off in the oxidation and received in the reduction, we can put that in. And this is Ln out here. Some students think it's an I or a 1 or something, but this is Ln. This is the natural log. So Ln, maybe that helps to see it that way. All right, and an interesting thing that comes out of this is that when the product concentration and the reactant concentrations are the same, say 1 molar, then that whole ratio of Q becomes 1. And then the natural log of 1 is 0. And then we would find that E and E naught are the same. I'm actually going to try to show you that in a little spreadsheet that I've generated that I'll have a link in Learning Hub, and you can go to my Google Sheet. We're going to play around with this equation so we can see what happens between E cell and E naught when things change. So I'm just going to pause a moment and bring that up. All right, I've loaded up a Google spreadsheet here that we're going to be able to modify the product and reactant concentrations in these little cells over here. So I'm going to come over to this part of the spreadsheet and start changing some numbers. Right now I have the product concentration as 0.2 and reactant concentration is 2. So I kind of have them on top of each other. And just to show you what the spreadsheet does, so here in this cell, I just do the division. Q divided is equal to P divided by R. In this cell right here, as I move along to the left, I actually take the natural log of Q. This is Faraday's constant. I put N in, whatever it is for the problem, temperature, and R. And I have the spreadsheet calculate all of this together as what I call a modifier. And then this is the electrochemical cell potential under standard conditions, just kind of a made up an example here. And then this is the final cell potential right here from the Nernst equation. So we want to kind of focus out here and see how things change when I change the product and ratio and the product and reactant concentrations. See what happens when I make the product and the reactant concentrations the same? Our modifier, which is that whole other part there, the 0.0257 volts divided by N, that all goes to 0. Why? Because you can see that here. I love that. So the Q is 1, and the natural log of 1 is 0. So that makes the whole term drop out. Now we can just start making the product concentration. Let's make it smaller and see what happens. So I'm going to cut it in half, and we see the modifier becomes a negative, but I'm going to subtract that modifier off, and that ends up increasing. Hopefully you can see that the overall cell potential goes up when the product concentration goes down, or another way to see that is there's more reactants than products. And so you can just simply just start changing these numbers. Let's make it 10 times the product concentration. And even at 10 times the product concentration, the cell potential is just slightly different from the original concentration or the original cell potential that's there. So this is kind of a fun little thing you can do. You can do this in your calculator, do it on a spreadsheet. I'll have a link in Learning Hub for you to see that. All right, let's go back to our presentation and see what we can learn next from this. All right, so it's important to understand what happens when you have more reactants than products. What happens to the E potential versus E naught? And I'm going to let my students kind of figure that out, and there'll be a quiz question in the attendance. See if you can figure it out. Does E become bigger, greater than the standard conditions, or is it less than? And then what happens when it's the other way around? You can use that little spreadsheet calculator to figure that out and to see it through. We kind of did it on the other one just so you could see it. All right, so let's switch gears here and talk about briefly a connection between equilibrium constant, delta G, and E. So how does the electrochemical potential kind of tie all of these things together? Let's see here. It's actually free energy that ties everything together. So when we look at and remember that our free energy at standard conditions is equal to delta G is equal to minus N times Faraday's constant times electrochemical cell potential, and we think back a chapter and we go, oh yeah, free energy is also equal to minus RT ln of K. Well, if A equals B and A equals C, well then B equals C. So we can set these two things equal to each other. And then if we divide both sides by negative NF, kind of like what we did with the Nernst equation, we can come up with this Nernst kind of looking equation that relates the equilibrium constant now to the standard electrochemical potential. So there's some important things to think about there now, because think about it. If K when we thought about equilibrium constants, we thought about K being greater than 1 and K being less than 1. These are our two main things that we think about. So K greater than 1, this is our product favored chemical reaction. When it's product favored, K is 1, ln of K then turns out to be a positive number, and then we would end up with the electrochemical cell potential being greater than 0. All right, then it's the other way around. If K is less than 1, we said these were reactant favored, and then we would end up putting a number less than 1 into the natural log function, and that'd give us a negative number, and we would get a cell potential less than 0, which is non-spontaneous. So a spontaneous chemical reaction has a positive electrochemical cell potential, and it has an equilibrium constant greater than 1. They're all the same ideas, just expressed in different ways. Electrochemical cell potential, energy, joules, kilojoules, and then in equilibrium concentrations. Same thing, same thing. We got to make all these connections between them. All right, because of this, something interesting pops out of the Nernst equation that we can, it's going to start to tie into some other properties of corrosion, batteries, and other spontaneous chemical reactions. This has to do with a concentration cell. What's a concentration cell? Well, it actually doesn't really have anything to do with concentrating right here, although it does take a lot of concentration to figure out this particular problem. But if you stay put, you'll be able to think it through as well. All right, what is a concentration cell? It is a way to make electricity to run and make a battery without having different metals. So in this particular problem, we're going to use the same metal in the same solutions. So we're going to think about having silver and silver ions, and we were going to have, and my pen's not working very well, and we're also going to have silver and silver ions on both sides, the anode and the cathode. And we're going to be able to generate voltage and make a battery, a galvanic cell, a voltaic cell, all the same thing. We're going to make that with the same materials. And this doesn't seem possible until we start thinking about how this could actually work. All right, so in our example here, we're going to actually use The Nernst equation help us predict what's going on. So for my students, have they done this before? Well, in the past, they would have actually done this in lab. You can create voltage in a potato, orange, lemon, something. When you stick in both metals, there is a small voltage in there. Why? It has to do a little bit with this. And the other thing that comes out of this is that you can generate voltage, a spontaneous chemical reaction, using the same metal and the same solutions. You'll see why that comes in there. So normally we thought about having two different metals, and that's typically true, but there you can generate a small amount of voltage, spontaneous chemical reaction with the same metals. And so what's going to happen is that one of the sides is going to act as the anode, and you're going to make cations. The metal's going to turn into cations. That's at the anode because of the oxidation. On the reduction side in the cathode, you're going to see some losing of the cations there. So there's going to be electrochemical change that will take place. Let's look at it in some more detail. So using the Nernst equation here, I got my pen back. The Nernst equation, if we look at this, we're going to assign, and I'll explain why, the cathode as the side that has the high concentration. Oh, so this is where the word concentration comes in. See, if you noticed here, this side is 1 molar silver ions, and this side over here, the anode, is 0.1 molar. So the difference is concentration. Those are terrible ones, but hopefully you can still see that. Let me get rid of those. Focus on the numbers on the screen there. So we have a high concentration and a low concentration side, and this makes all the difference. And we're going to assign the high concentration to the cathode and the low concentration to the anode. Well, in this particular setup, the electrochemical cell potential is 0 under standard conditions. Why? Well, they're going to have the same concentration then. They would both be at 1 molar. And if they're both at 1 molar, Q goes to 1, ln of Q goes to 0, that whole thing drops out, and we would have 0 altogether. So that's no good. So by switching the concentration, we can actually create a Q that's not equal to 1. In fact, it will always be a number that's favorable here to give us a positive voltage. How is that? Well, whatever side is the highest is going to act as the cathode. Whatever side is the lowest concentration is going to act as the anode. And we're going to put the anode, the low number, in at the top, and it's going to give us a Q. When you divide a small number by a big number, you're going to get a number less than 1, and that's going to create a natural log number that's negative. And then when we plug it in, we're going to end up getting a positive voltage. So this thing will always work in one way to give a positive voltage. So how do we know that the anode is the low concentration, the cathode's a high concentration? Let's think it through. So you see at the anode, there's oxidation that's taking place. So anions are needed from the salt bridge to come in. So anode, anions needed because cations are being made there. That's why the anions are needed. So if cations are being made, they're actually being produced. Produced means product. The concentration is increasing on the silver, and the silver concentration will be increasing here. So if you're making them, then that means they're the products, right? That's what those words mean. On the cathode side, we're actually consuming cations. So the cations actually are needed to come over on this side. And so since the cations are reacting on this side, they're gaining electrons, that means they're reacting, and they become the reactants. And so the concentration of silver is actually going to go down on the cathode side. Now, if we put this all together, see, these are the reactants and the products. So I know they're going to switch here. The concentration of the silver ions that are large or high, those are on the reactant side, and the anode are on the, and it will switch. If you were to switch them around, then these would switch. So the side that's always the highest concentration, the cathode here, so this ends up, and my pen doesn't want to write again, and hopefully you can see that the reactant side. So that's why the reactants ends up as, in our equilibrium expression, the cathode numbers end up, they're the big numbers, they end up at the bottom, because they're going to end up going away. It's practice. Let's say you got a concentration cell using 2 nickel electrodes, which means you have a nickel metal on one side, a nickel metal on the other side, but now you got two nickel concentration cells there. Calculate the potential of this. All right. So one of the keys is to go, wait a second, I'm switching the concentrations there. Got to use the Nernst. All right, so let's jump in and see how we can figure this out. So remember now, the high concentration side is our cathode. The low concentration side is the anode. And another reason to think this through is that the cathode side is going to lose potential, and then the other side, the anode, is going to gain until the concentrations come into equilibrium. And that means they're going to react until the product and the reactant side concentrations are equal to each other. That means they're going to equal 1, Q will equal 1, and if Q equals 1, ln of Q equals 0, and that whole Nernst part of the modification term drops out, and then there's no potential. So they won't always react for on, you know, into eternity, but they'll stop at some point. So if we were to plug in those numbers, I did it here. I'm sorry it's all up there, but we'll kind of walk through the steps here as much as we can. Let's see if we can, my pen's not letting me react here and write anymore. That's all right. So as we try to think this through, line 1 here, this cell potential under standard conditions is 0. So that's going to be easy to figure out. Now we just got to worry about the modification term here on the Nernst equation. It's nickel plus 2, so then that's where we get 2 electrons are going to need it to turn this from nickel plus 2 into nickel solid. So we can put 2 in for the N. What are the concentration of the products divided by the reactants? Well, the anode is the low concentration side, so we're going to put in 1 times 10 to the minus 4 for our product. And then the reactants then are the high concentration, 1 molar. And when I do the math, Q equals 1.0 times 10 to the minus 4, plug that in, and then I can generate a 0.117 volts. Not a lot, but the key thing here is that it is a spontaneous chemical reaction generating a little bit of voltage. Good. All right. Now, in your OWL homework, you're going to come across something weird like this, because not all chemical reactions are in these concentration cells are going to look exactly like this. So here's a question. What is the calculated value of the cell potential at 298 for an electrochemical cell with the following reaction? So this one actually is not quite a concentration cell, but something weird you're going to come in contact with. When the hydrogen pressure is 2.4 times 10 to the minus 3 atmospheres, and the hydrogen concentration is 1.05, and zinc concentration is 2.07 times 10 to the minus 4, here is our chemical reaction, hydrogen ions plus zinc to give you hydrogen gas and zinc ions. What is Q? How are we going to figure this out? So we want to think about this option here. How would we set up Q? Well, I have some options here. I have Q set up where you just put in the concentrations. They gave us a few concentrations. Oh, but one of them is in atmospheres. Well, maybe we should switch them all to atmospheres, or maybe find a way to switch concentration and the pressure. So would it be A, B, or C for us to figure this out? Well, it turns out C is actually, and this surprises our students every year, we're going to end up using C to calculate our Q. So when there's a mix of pressure and concentrations, we leave them mixed and we just put them into our Q to figure it out. And I have, so I actually do that. In this particular example, you just leave it. And so Q equals the pressure of hydrogen times zinc divided by hydrogen ion concentration. Now we don't put the zinc solid because that doesn't change its concentration. And so I actually go and figure out this particular half reaction right here for you, or this reaction and the voltage that is there. So why is this so important? Why is a concentration cell, Nernst equation, and these things so important? Well, the answer lies in this spontaneous electrochemical reaction called rust. Oh my, the most feared, we call it Michigan cancer here with automobiles and so many other things. Rust is a spontaneous oxidation process that has a lot to do with the Nernst equation and reactions that occur with the same metal here. And all of this information that we've been learning about electrochemistry is going to give us the foundation, the tools now to go and appreciate batteries a little bit more and appreciate corrosion and corrosion resistant materials and how scientists use this information to better the world around us. So hopefully you've learned a few things about electrochemistry that you can use to solve your problems and to see the world in a different way. I'm Dr. Ryan Hayes. Thanks for joining me.